Hello everyone, my name is Gary Skanderi and today I'm here to present MovingFashion, a benchmark for the Video to Shop Challenge, a work done by my colleagues and I at the University of Verona. In our paper, we explore the video to shop problem, which is the problem of matching one or more clothing items appearing in a video against an image gallery. This is appealing for social media videos because of celebrity or influencer outfits, but it is of course a challenging problem. Information in video frames can be noisy, very often because of illumination, zooming, and human poses, and also because current video to shop systems require training data with millions of bounding box annotations, which in practice is often not feasible. To this end, we propose MovingFashion, the first open data set for the Video to Shop challenge. It's made up of approximately 15,000 unique videos and 6 million annotated frames, and it contains 15,045 video to shop pairs. It is formed by two subsets, regular and hard. The regular subset consists of 10,132 videos downloaded from the e-commerce website Net-a-Porter. This subset represents the easier challenge in MovingFashion because, of course, the videos are taken in a controlled environment. They're just meant to depict the clothing apparel that Net-a-Porter is trying to sell. As such, the challenge is, of course, easier. In the hard subset, on the other hand, which is made up of 4,723 videos downloaded from social platforms like Instagram and TikTok, the challenge is much more difficult because these videos contain several people and also several clothing items where these people are not actually trying to actively showcase the clothing items. We make use of MovingFashion to train an architecture we dub SEAM Match RCNN, which stands for Self-Attention Multi-Frame Match RCNN. Of course, this architecture is built on top of the Match RCNN architecture, and it allows us to not use bounding boxes. The two main blocks that make up the architecture are the Match RCNN and the multi-frame matching head. The training procedure uses pseudo-labeling in order to learn. In phase 1, we train on the source domain, which is Street to Shop, where we use the Deep Fashion 2 dataset. Here, the Match RCNN learns to estimate bounding boxes and also estimate matching scores. Then in phase 2, we use this pre-trained Match RCNN to do what we call tracklet generation. A tracklet is defined simply as a sequence of observations in the video that contain the same detection or the same clothing item. To generate a tracklet, we first choose a pivot. That's the box that matches the best with the shop image, or the frame in the video that represents the shop image in the best way. We then propagate this pivot along the other frames. This simply means that we're trying to match the pivot frame with all the other frames available in our video so we can understand in which frames the pivot box is actually appearing. Once we create the tracklet, we can then use our multi-frame matching head, in which we use first a non-local block to perform self-attention and then a cross-attention mechanism among all of the frames in the tracklet. This allows us to create a weight for each frame, which then can in turn allow us to perform a weighted mean of the representations of the boxes in each frame. This gives a unique descriptor W, which we can then use in our f tilde function to then pass to the matching function. In the end, we get a matching score, which is in the range of 0 to 1. This tells us how similar or how much a tracklet is matching with a shop item. This also allows us to create a ranking of the items. Because the scores are in the range 0 to 1, we can actually match the tracklet with all of the items available in the gallery and hence get a ranking of which items are appearing in the video. Here you can see some quantitative results of SEAM Match RCNN. You see how our architecture performs best in both top 1, top 5, top 10, top 20 retrieved items. Also, you can see the contribution of both attention blocks, which are the non-local block and our cross-attention module, as the performance of the model deteriorates if we do not use these modules. Here you can see some qualitative results where on the left side on the screen, we managed to find the correct item appearing in the video in the top 1 retrieved items. On the right-hand side, you can see how we're computing the weights, and when discriminative features are not showing in the video, the weight drops down. In conclusion, MovingFashion provides a new benchmark for the Video to Shop challenge and a new state-of-the-art baseline, which is SEAM Match RCNN. Unveiling fashion trends is just one of the many possible applications of our approach. Thank you very much for your attention, and don't hesitate to contact us if you have any questions.